Hello, this is Jingcheng Niu, or you can call me Frank. So let me ask you this question. Does BERT really rediscover a classical NLP pipeline? Jawahar and Tenney think it does. Through their probe, they believe that the allocation of linguistic information in BERT follows our general understanding of the depth of those information. Just as Jawahar et al. Have said, surface information at the bottom, syntactic information in the middle, and semantic information at the top. And this structure of information is really similar to a discrete pipeline-based NLP system, where surface information, such as tokenization, etc., is processed first, and the result of those processing is passed along the pipeline until we can get a deeper understanding of the text. Therefore, there's a claim that BERT has rediscovered the classical NLP pipeline. However, this classical NLP pipeline probably doesn't exist, or at least it's an oversimplification of psycholinguistics and cognitive science research from the 1970s to the 1990s. But how did they draw their conclusion? And is their evidence strong enough? To answer those two questions, we conducted a reappraisal of those two really influential works. Jawahar et al. Used a performance-based probe, so they used tasks from Sentinel, and there are 10 tasks in total, ranging from 3 different linguistics levels: surface, syntactic, and semantics. And then they trained probes with access to only one layer of BERT's embeddings, and found this general trend that deeper tasks perform better on upper layers, and shallower tasks perform better on lower layers. However, if we ignore surface information for now, it's not really clear whether we can say that this trend still exists. Syntactic and semantic tasks perform the best on roughly the same range of layers. Besides, the performance difference between layers is very small. Take the 10 tasks as an example. The performance of layer 5 and to layer 12 are really similar to one another, and the biggest delta in this whole range of 7 different layers is only 0.5%. And therefore, we plotted this heat map to better visualize the results. The darker the color, the closer the layer's performance to the optimal layer's performance. And as we can see, there is this large dark area for syntactic and semantic tasks. And this suggests that while surface information locates at the bottom, we can't really tell syntactic information apart from semantic information. And to verify this, we ran a Kendall's tall test on Jawahar et al.'s result. And just as we had suspected, we found a moderate correlation when we include surface tasks, but only a very weak correlation when we only consider some syntactic and semantic tasks. And this confirms our observation that syntactic tasks and semantic tasks perform better near the same range of layers, and their performance patterns are not distinguishable by layers. So the arrangement of BERT information is something more like this giant BERT head instead of a pipeline. And Tenney et al., they used a different attention-based probe. They added a self-attention module to their probe classifiers and interpret the attention weights as feature importance. As we can see on the right, the attention weight distribution roughly followed the same trend Jawahar et al. Have found, which means deeper information on upper layers. However, the last two tasks, SPR and relation information, the attention weights are basically flat. And then they calculated the center of gravity of those attention weights and observed a trend similar to what Jawahar et al. Have found. Again, they did not conduct any statistical analysis of the trend, so we calculated the Pearson correlation between the tasks and only found a really weak correlation. So the question of whether BERT has rediscovered a classical NLP pipeline is still inconclusive. But we believe that we can have a better shot at this question if we can have a better probing method. And using this probing method, we can also have a better understanding of the internal workings of BERT. But before I start to introduce our probe, I want to talk about some of the problems with Jawahar and Tenney's probing methods. And the immediate problem is that the performance of neural networks is inherently numerically unstable. So we have talked about this for a little bit. The performance of the probe on different layers are really similar to one another. So can we really say that layer 9 is definitely the optimal layer? It is very possible that layer 6, 7, 8, or 11 may have a better performance in a different run with a different random seed. And secondly, there is always this question of whether we can use supervised probe classifiers' performance as solid evidence. So as Hewitt and Liang has pointed out, when a probe achieves a high accuracy, can we conclude that the representation encodes linguistic structure, or has the probe just simply learned the task? So we think Tenney et al.'s attention-based probe is more suitable for this task. Generally speaking, attention is proven to be a good indicator of feature importance, and we can use the attention mechanism to understand how the layers encode linguistic information differently. And that being said, Tenney et al.'s probe is a bit limited by their probe architectural design. So they use a shared set of attention weights for the 12 or 24 BERT layers for every single input sentence. But as I will show later, the model may attend to different layers for different sentences. And this architecture cannot capture this variance across different sentences. And this variance turned out to be a really important nuance of the structure of BERT. And finally, they force the probe to look at only one or maybe two span representations in the sentence, so we can understand the layer attention pattern, but we cannot understand which token position gets more attention. And as we will discuss in a moment, this token position attention pattern is very interesting, and they are also very different from task to task. But those two limitations are actually solvable. In fact, this method of self-attention pooling by Li et al. Is used by Tenney et al. To calculate the span representation. And the idea is actually quite simple. We can use a feed-forward neural network. For example, in our case, we use an RNN, and use it to assign an attention score to each of the tokens. And when the size of the feature is not changing, just like we would know that there will be either 12 or 24 different layers in BERT, we can use the same method but use a fully connected layer to dynamically assign different attention weights to different inputs. And this forms the basis of our GridLoc probing architecture. And this architecture solves all four aforementioned problems by probing across three different dimensions. The first problem is that performance is inherently unstable. We solve the problem by probing along the randomness and training time dimension. And we repeat all of our experiments 20 times, each with a different random seed, and record the results of all 30 different epochs. And then, to answer Hewitt and Liang's criticism, we use an attention-based probe just like Tenney et al. And to capture the variance across different sentences, we use the self-attention pooling method to collect sentence-specific layer attention. And finally, we use the same method to enable us to observe the probe's attention to different token positions. So just a quick recap, when we obtain the input sentence entire encodings, we first use an RNN to perform self-attention pooling and get the token position attentions for each of the layers. And then, using that attended result, we can calculate the layer attention score. And using this method, we can get the average attention weights for every centivolt task. And as we can see, most of them follow this bell curve shape. But different tasks have different peak layers and different dispersions. Also, we can't really tell syntactic tasks apart from semantic tasks. So, we run the same Kendall's tall test on these results, and we observe a similar 0.503 moderate correlation. And again, if we exclude the surface task, we can only find a next to nothing 0.134 correlation. So this is similar to our reappraisal of Jawahar and Tenney et al. That there isn't really a strong classical NLP pipeline in BERT's layers. And those token-wise attention patterns are the result of taking the average of all of the sentences in the test set. But if we break down our results by each sentence, the attention weight distribution of each individual sentence may not follow the same pattern. For example, here are the layer attention weights of the first sentences of the background shift task. So same probe model, same epoch, same task, same everything, but very different attention weight distribution. And to aggregatively look at this variance, we computed the standard deviation of the best performing layer of all of the sentences in all of the tasks. And in all but two tasks, the standard deviation is one full layer or more. Then let's look at varying through randomness. And here are the distribution of the best performing layers of every sentence from two different random seeds. And we can definitely see that they're pretty different. And this means that the probe results are not immune to randomness. And finally, here's the attention weight distribution of the SOMO task on C0 across different training epochs. Even the best epoch is only a snapshot in the training process, that the layer attention is constantly bouncing around, and it is not stabilizing over some layer distribution. And the layers actually never make up their mind. Instead, it's actually we tell them that where to stop based on performance. So the structure of BERT is an illusion from aggregation, and if we look closely, the structure of BERT layers is more dynamic and random than we previously understood. But there is one thing that is more constant, and it's token position attention. For each of the thumbnail, each vertical row is a BERT layer, and each column is a token position. And the brighter the color, the higher the attention score. And for most of the sentences, the token position attention at every layer attends to the same token, hence the bright vertical lines. And the choice of those token positions is not random. There are linguistic reasons behind them. So let's see 3 examples of linguistic reasons. First, take sentence length as an example. Because sentence length is a sentential feature, the probe will focus on the CLS token. And second, for the word content task, it's a task to see whether a pre-selected list of words exists in the sentence. And if there is actually the word, the model will focus on that word. And finally, for the tense task, the probe will focus on either the verb itself or its tense-bearing word piece. And noted that all of these plots are normalized by layer, and so each row sums up to 1. So in another word, we are trying to observe how each layer assigns attention weights to every token position. But when we normalize the attention pattern by token position, meaning now we normalize it such that each column sums up to 1, then we can't find any obvious patterns anymore. So is the pattern more obvious for token positions or for layers? Can you see horizontal lines for layers, or can you see vertical bright lines for token positions? Therefore, unlike the unstable probing results for BERT layers, the distribution of attention along token position is relatively more stable. And as my supervisor always says, probing was like a box of chocolate. You never know what you're gonna get. And we got tree depth. The bright vertical line pattern doesn't exist anymore. Instead, the bright spots are all over the place. However, if we look into the patterns of those bright spots, we found something that is really interesting. So different parts of speech, for example prepositions like on and at, light up at lower layers, but punctuations like comma and period, they light up as upper layers. To confirm this finding, we calculate the average most attended layer for tokens with different part of speech tags. And they are really different. Punctuations on nouns are on layer 7, and prepositions is only on layer 3. And to make sure that this average layer result is not a fluke, we computed the point by zero correlation between all the tokens from each pair of part of speech tags. And we found some pretty high correlations between punctuations and prepositions, adjectives and prepositions, etc. And also, those correlations are all really significant, with p-values smaller than 10 to the negative 323. So, because part of speech information is certainly not self-evident in a corpus labeled with tree depths, we can answer Hewitt and Liang's question. It is not the case that the probe classifier simply learned the supervised data. There is certainly some linguistic knowledge in BERT. However, what we see here is not Jawahar and Tenney theory that different levels of linguistic knowledge from the pipeline occupying different layers of BERT, but rather different information from the same pipeline level, for example in our case distinct part of speech labels occupying different layers of BERT. So did BERT rediscover a classical NLP pipeline? Not really in a naive architectural sense. Probing results regarding BERT layers are still really unstable. However, distribution along token positions is relatively more stable. And we believe that this pseudo-cognitive appeals to layer depth may not be the best way to explain BERT's inner workings. And finally, tree depth gave us evidence that the distributions of linguistic features in BERT doesn't really follow Jawahar and Tenney's theory. We didn't really see different levels of linguistic knowledge from the pipeline occupying different layers of BERT, but instead we found evidence of different information from the same pipeline level, in our case the part of speech information, occupying different layers of BERT. And this concludes my talk. Thank you so much.